Hello, everyone. We're going to be looking at Chapter 7a, which is our revision of some matrix algebra. We're really just going to be looking at addition, subtraction, and multiplication, both by a constant and by some kind of scalar quantity. You can see there's a whole stack of notes here. Feel free to have a quick skim through there. There's also some calculator help. So instead of going through the examples, I thought let's just look at the general ideas. This is revision. So I think if I just kind of refresh our minds as to how we do this process, I think then you guys can not only do the examples, but also do the questions as well. So let's start off with matrix addition and subtraction. The reason these two are paired up is much like in mathematics, the processes are very, very similar. For matrix addition, there's two ways to think of it. One of the ways is I can put letters in here, and I think when we first looked at this, we used letters. Let's just call this A, B, C, and D, and we'll call this E, F, G, and H. So if I'm adding two matrices and these are my individual elements, and just to recap on some terminology, I call my entries into a matrix, or my little parts, I call these bits elements, my little parts I've highlighted in yellow. Also, just note, the way I define a matrix is based on their size. Now, these are 2 by 2 matrices, but one of the ways to define it is this idea of M times N, which refers to the idea of I have M rows and N columns. So I define the size of my matrix as being my rows times my columns, which hopefully we all can remember it, and that all makes tons of sense. So I've got rows and columns, so I define my size. These are both 2 by 2 matrices. A lot of the work we did in year 11 was focusing on 2 by 2 matrices. This time around, we will introduce some 3 by 3 as well. However, all those 2 by 2 matrix skills we still need to have retained. So if I'm adding these matrices, well, the answer to this type of question is simply just going to become A plus E, B plus F, C plus G, and D plus H. In other words, when I'm adding matrices, I do kind of my first element by my second element, my third elements add, and my fourth elements add together. Now, if I'm subtracting, this process is exactly the same. So if we look at the exact same question, if I change this addition to a subtraction symbol, then all I do here is I change all of these symbols to a subtraction symbol, and the process is exactly the same. So addition or subtraction, I can just add my corresponding elements in my 2 matrices. This works for 2 by 2 or 3 by 3. Just note, both matrices have to be of the exact same size to add or subtract any matrices. Okay, so we've done addition and subtraction. Now let's have a look at matrix multiplication and division. I put division in quotation marks because we can't actually divide matrices, and I'll kind of show you guys what I mean by that. So if I have 2 matrices and I don't put a symbol in between them, I assume I'm multiplying. So when I'm multiplying matrices, we don't tend to write the times sign. We just write our 2 matrices next to each other, the same way we write algebraic letters. Just know we also label matrices with capital letters. So this could be called matrix A, this could be called matrix B as an example. So if I was to write this, I would simply just write AB would be the operation of A multiplied by B. So if I see AB, it's A times B. Again, we don't write our multiplication symbols when it comes to matrices. So if I have 2 matrices like this, and let's just give them the exact same names, A, B, C, D, E, F, G, H. If I'm referring to the size of these matrices, when I'm multiplying matrices, there's a little big note we need to make here. To multiply matrices, columns of A have to equal rows of B. In other words, if I have 2 columns here in this matrix, then I need to have 2 rows in this matrix here. So my columns need to equal my rows. Also, if I'm defining the size of these matrices, this is a 2 by 2 matrix. This is a 2 by 2 matrix. Again, my column needs to equal my number of rows. So because these 2 numbers here are the same, then I can multiply the 2 matrices, and the size of the result of this multiplication is going to be a 2 by 2. So the inside numbers need to equal for it to multiply, and the result, or the size of my matrix, if I do my multiplication, is going to be the outside 2 numbers. So this is size, and the yellow tells me if it's possible to multiply. So that's kind of, again, just covering off those base ideas. To multiply two matrices, my columns need to equal my rows. Or my columns of A need to equal my rows of B, again, assuming I've labeled this A and this B. So in terms of how we actually do our matrix multiplication, to do our matrix multiplication, I multiply row by column. So this row here will multiply by this column here. And I'm going to do some addition. So it's going to become AE plus BG. It's going to be the first entry of my new matrix. Now I'm going to take that same row, I'm going to multiply by this column here. That's going to become AF plus BH. That's going to be the first row when I'm multiplying my two matrices. Once I've done my first row by my two columns, now I'm going to do my second row by my two columns. So now CD is going to be multiplied by EG. So that's going to become CE plus DG. And then if I do it the second time around, CD times F and times H is going to become CF plus DH. So if I'm multiplying any matrices, my columns must equal my rows. Then I multiply row by row versus column by column to get my entries, and I'm adding those two separate terms together. A good thing to note is if I was to swap my order around and I was to do this multiplication, I would get a different matrix. So if I do A times B, it is not the same thing as B times A. I get a different answer. Have a quick think, or if you want, you could actually try to do B times A. You'll see you get a different letter combination in our result here for our solution. So the word we use is not commutative, which means A times B does not equal B times A. So my order is important when it comes to multiplying two matrices. For the division part, for my matrix division, like I said, I can't really divide by matrices. So one of the ways I can think of dividing matrices, if I wanted to divide matrix B by matrix A, and normally we'd write our division like this as some form of fraction. However, in this particular case, like I said, I can't really divide matrices in the same way. So instead, I'm going to express this in index form. Well, this is going to equal the same thing. This is going to be A to the minus 1B. So to divide our matrices here, I apply the inverse. So you can see A to the minus 1 is called the inverse. We've looked at finding these inverses before as well, and we'll look at finding inverses in the next lesson. I just wanted to kind of point out, to divide matrices, I apply the inverse of one of my matrices. That's kind of the concept of the idea. We're going to look at this in a little bit more depth in the next lesson of how to actually find our inverses and how we can solve problems using our inverse. But for now, matrix division can be thought of as finding the inverse of one of my matrices and then just multiplying it by the other matrix. So the final thing we're going to look at is scalar matrix multiplication and division. And again, division is in little quotation marks because we can't technically divide, but the mathematical process will essentially be the exact same. So if I have matrix A, and again, we use capital letters to notate or denote our matrices, and I put the number 3 in front of matrix A, and let's say matrix A is equal to A, B, C, D. So the similar thing to before. If I put a 3 out the front, I simply just put a 3 out the front of my overall matrix. What this means is that number 3 is going to be multiplied by each individual element of my matrix. So if I wanted to kind of expand out what I have, my result would be 3A, 3B, 3C, and 3D. Now we see I've got a common factor of 3 here on all my terms. So the more simplified answer is to write it like so. And if I was simplifying my matrices, I would take that 3 out the front. However, I can multiply by a scalar quantity. Sometimes it's easier to put my 3 inside my matrices and do operations that way. Or sometimes the question just requests you to do some form of scalar multiplication. So it's good to know that this process is possible. To do division, I can't really divide A by 3. It doesn't quite work out that way. But as a similar idea, division really, I could write this as being 3 to the minus 1 times A if I do a similar idea to before. Well, 3 to the minus 1 is simply equal to 1/3 A. So division, and I think I spoke about this idea last year, division is actually the same thing as multiplying by fractions. So dividing by 3 is the same thing as multiplying by 1/3. So to do matrix division, it is essentially a scalar multiplication, but my scalar quantity is just less than 1. It's going to be some fraction. So same idea now, if I have A over 3, that is going to be equal to A over 3, B over 3, C over 3, and D over 3, if I put that back into my matrix. So hopefully that was helpful as a quick recap. Like I said, we're going to look at inverses in the next lesson. That is going to be 17b. You can see inverses, determinants, all that stuff, which is also going to be a bit of revision.